So, in the last lecture we discussed about the derivation of stiffness and mass matrix for TLP. So, we already know how to derive the mass matrix and the stiffness matrix from first principles for a tension like platform. So, for a given equation of motion, as we see here, we already know these elements, and of course we believe that we know how to compute f of t for a given geometric form, for example for a TLP, and we will be focusing on how to estimate C in a couple of lectures from now onwards. So, people generally use what we call classical damping for estimating damping characteristics in structures. Classical damping can be applied if you have uniform distribution of damping for the entire structure. If you have uniform distribution for the entire structure, then you can go for a classical damping. Now, this is true for offshore structures. This is true because we have damping which dissipates the energy produced by vibration of the structure in the water body. So, it is more or less uniform. So, we can always try to work out a classical damping for offshore structures. Now, there are two ways of looking at the classical damping. The literature suggests one can go for Rayleigh damping, the two cases we will discuss in the successive lectures. In this lecture we will talk about Rayleigh damping. We already know that damping can be either proportional to mass or proportional to stiffness. For example, my damping value can be a proportional value with respect to mass, or it can be a proportional value with respect to stiffness, because essentially the dissipation happens either from the mass interference or inertia interference or from the restoration interference from the elasticity of the material or the member. We will try to plot this graphically. Let us see how does it look like. If I have a structural system like this, I am just taking an ideal stick model. This can be also similar to a jacket structure or a TLP, anything. This discussion does not hold directly related to a TLP now. I am just offlining from TLP, I am discussing a classical damping theory first, then apply it to TLP and show how this can be done. So, I have got, let us say, a 3-degree freedom system model which is a conventional stick model. So, the damping can be graphically represented like this. So, there is a pseudo frame which is fixed to the ground or fixed to the foundation, and I have a damping applied which dissipates the energy caused because of vibration of this model, which is proportional to the respective mass which is lumped at the respective locations. Now, where this has come from? The source for this model, if the structure is not offshore, it is onshore, let us say, then the source comes from air. Okay, the damping has to come from air actually, is it not? So, this can be relatively low if it is in air, right. So, this model of proportional damping with respect to mass and inertia force, if the model is in air or maybe in onshore, then this can be relatively low. In our case, this is relatively higher because majority of the structure is retaining in water. Okay. For example, gravity structures, it may not be true for a TLP because partly it is in water, but majority of the structures like gravity structures, ATs, etc., guide towers, they are in water. We have got phenomenal representation of this. So, this can be applied. Alternatively, if you look at the stiffness proportional model of damping, it looks like this. Let us say I have again a 3-story framed system whose stiffness are indicated as K1, K2 and K3. With respect to the inter-story displacement, the relative movement of each floor or each mass position, with respect to the relative movement of each mass position, you get damping, which is A1 K3, A1 K2 and A1 K1. So, this depends on the inter-story drift, what I call, or the relative movement between the mass points. The relative movement between the mass points, because these are the points where the mass is lumped. This is true because if you take for example a multi-legged articulated structure, if you take for example a TLP, you will find that the mass is being lumped between the stiffness elements at different location and they are allowed to move independently because of the hinge in between them. Okay. So, we can use this model. Now, both of them are relatively applied to an offshore structure, but let us see what are the difficulties if we apply alone mass proportion or K alone. Let us see what happens to this and why Rayleigh is invoked. Okay. Rayleigh model or Rayleigh damping is not, Rayleigh damping is neither mass proportional nor stiffness proportional, a combination of these two. Okay. Let us see what is the difficulty when I use this independently. So, we know Cc is 2 zeta omega m, is it not? It is a fundamental thing which we already know. Equation 1. We also know let Cn, I am instead of saying critical damping I am saying Cn, which is now taken as A0 Mn. So, zeta will be A0 Mn by T omega Mn and omega n, where I say zeta n, which will amount to A0 by 2 1 by omega n. It means zeta n is inversely proportional to the frequency. It is inversely proportional to the frequency. If I try to plot this, zeta n, it will be non-linear. This is how it will going to look like. So, what we say is A0 by 2 1 by omega n. This is actually mass proportional damping, and we can also note that the damping ratio is proportional to, or we can say the damping is proportional to modal damping ratio. C is proportional to a specific omega and zeta, is modal proportional modal damping ratio. So, I call this equation 3. Therefore, A0 will be 2 zeta n omega, or let us use a different suffix here. Instead of saying natural frequency, any mode, ith mode will give me A0. So, once A0 is determined, one can easily find C. Hence, C, which is A0 m, can be computed because A0 is known. Similarly, let us try to see for stiffness. For stiffness proportional damping, Cn is A1k, which is A1 omega square m, and C we already know it is 2 zeta omega n. C is 2 zeta omega n. So, zeta, which is C by 2 omega n, which is A1 omega n square mn by 2 mn, which is nothing but A1 by 2 of omega n. So, it is directly proportional, which is again linear. So, this is my stiffness model, which I get this as A1 by 2 omega n. So, very interestingly, if you pick up a mass proportional damping for a higher frequency, I get lower damping. If I pick up stiffness proportional damping for higher frequency, I get higher damping. So, it has been seen in the experimental studies, the literature, which I give the references later, that neither of these models hold good for experimental determinations, because people have estimated damping ratio by conducting physical model studies on different structural members and tried to apply free vibration test and find out the damping ratio from the response of the structural system and compared that, and they have seen that neither mass proportional nor stiffness proportional alone will qualify the results what we got experimentally. So, the critical comment here is experimental observations do not agree with both independent models. So, Rayleigh said let us combine this. Which is going to be a combination of mass and stiffness. This is equation 7, 6 I think I missed out somewhere. Therefore, the damping ratio can be given by A0 by 2 of omega n, A1 by 2 of omega n. Now, the problem is how to get this A0 and A1, or how to get select the specific omega. So now obviously if you try to plot this for different values of omega n versus zeta, the curve comes like this. It closely agrees with the mass proportional, then it starts agreeing with stiffness proportional. It means at any specific value of zeta, I must have natural frequency system of two values which agree for the same zeta. So I must pick up those frequencies in my given system which agree for the same zeta. Okay. So it is an iterative thing or it is a guess. Select for example zeta 5% and see whether all frequencies do agree or match in the closer range of zeta is equal to 5%. So it is very interesting that we must first find out omegas for a given system, pick up zeta and pick up any two frequencies to find out them A0 and A1, because there are two equations, you need two unknowns and two equations, pick up them, find A0 and A1, which I will give you the equations now, we will derive them. I get A0 and A1, I get C. Then I apply that C or zeta for the third frequency which I have not picked up so far, because my degree has got 3 degrees of freedom, let us say my model. I picked up two frequencies, I saw that they are agreeing, I want to check do they agree for the third one also. If they agree in the closer range of zeta, then this model can be applied easily for my structural system. Okay. Now a question may come, if you have got infinite degrees of freedom model, it is a very large number, how do we pick up a zeta for a specific value? Then we can apply the third concept what we are going to discuss later. I can pick up damping ratios for different modes separately and use modal superposition for damping. I can do that, but unfortunately in our problem of TLP or in offshore structures we have a limitation of let us say 6 degree freedom system model for rigid body. Okay. So we do not have that large number of omegas to be discussed, but one can do this also, which I will discuss in the later part. So the argument here is I must pick up omega I and omega j such a way that they agree for a constant zeta. Okay. To get a constant zeta or equal zeta at different omegas, let us try to find out what are those governing equations which will give me A0 and A1, because if you know A0 and A1 using equation 7 I can find C, is it not, because M and K are known to me. Is that clear? So I must have a governing equation now to find out A0 and A1 for a zeta which agrees for omega and omega j. Is that clear? This is what Rayleigh damping is. Now let us get these equations. I will take away this. Yeah, you must select closely spaced or widely spaced or enough spaced omega such that your zeta has a common agreement between two omegas of your choice. In a given 6 degree of freedom, omega 1, omega 2, omega 6 can pick up any two omegas such that zeta is agreeing for that. I will demonstrate an example here and show how they agree, how they do not agree. Okay. So you have got to keep on changing zeta in such a manner that they agree for almost all frequencies which you are interestingly to contribute. Okay. But in TLP you have a greater advantage, you have got only two set of frequencies, one is either very high or one is either very low. So I can easily handle this model of I and j in my problem for a TLP, because I have divided the system in such a manner I got only two groups of frequencies, either very high or very low, either very high or very low. Probably it may agree on a specific zeta, we do not know actually, we have got to try that. Okay. That is guess. Given omega 1, 2, 3, 4, 5, 6, should I say 1 and 3, 2 and 4, 1 and 6, that is guess. That is guess, we have got to try that. Okay, which 2 degrees? Generally you should not pick up closer values, okay, just for agreement. Okay, omega 1, omega 2 are very close, pick up these two, then you are missing. The whole idea is the zeta should represent larger range of frequencies, that is the idea. That is the idea, is it not? Suppose if you do not have a larger range of frequencies at all, your whole frequency of a structural system is focusing only on a small zone, then I want to include zeta for all the frequencies, then also we have an option, but not using Rayleigh. Rayleigh's idea is you must spread this for the entire structure. that is the idea. Okay. So, I want to get the governing equation for A0 and A1, let us quickly do that now. So, let us say zeta I am expanding equation 8 now, zeta I is A0 by 2 1 by omega I and zeta j is A1 by 2 omega j, is that okay? And we all know that zeta n is nothing but A0 by 2 1 by omega n plus A1 by 2 omega n. Let me call this as equation number, let us say 9a. Let us expand it, zeta I zeta j half 1 by omega I 1 by omega j of A naught A1, is that okay? I am just writing in a matrix form. I call this as my matrix A. I want to find A naught and A1, I will invert this matrix, multiply with zeta, get A naught and A1, okay, get inverse of this matrix A. So, twice of determinant of omega j by omega I minus omega I by omega j of omega j minus 1 by omega j, no sorry, minus omega is it, yeah, okay. I will remove this, write it here, yeah, minus 1 by omega j minus omega I 1 by omega, that is my inverse. This is j, this is also j of course, I think I will write it with more clarity, this is j. So, omega j minus omega I minus 1 by omega j and 1 by omega I of, now I have two zetas which are same, I can put zeta and zeta to get A naught and A1, is that okay? So, can you give me the equation for A naught? Simply multiply this in a proper format. So, that is going to be equal to, we can write this as A naught A1 is going to be equal to 2 omega I omega j by omega j square minus omega I square of this matrix of zeta and zeta. So, A naught will be equal to 2 omega I omega j square I square of omega j zeta minus omega I zeta, is that okay? So, I simplify this, I get twice omega I omega zeta by j minus I of zeta. Okay? I call this equation number 10. Similarly, A1 will be 2 omega I omega j by omega j square minus I square of minus 1 by, okay, 1 by omega I minus 1 by omega j of zeta. which will be 2 omega I omega j square minus I square of omega j minus omega I by omega I omega j of zeta, and this can be again cancelled. I will get this as omega j plus I of zeta. Is that okay? That is my A1. I call this equation number 11. Now, from equations 10 and 11, we know A0 and A1. Let us see how. If I know two frequencies j and I, if I assume zeta any value varying from 2% to 5%, any value, find A0 and A1. If I know A0 and A1, I can find C as simply this. So, that is what my idea is, to get damping matrix. Now, what are the problems associated with this particular method? Any doubt here? Any doubt? Any doubt? So, we will be able to get C matrix because I know A and M and K already. I have computed A0 and A1, so I can find C matrix. So, there are some specific observations of this method. 1, you must select omega I and omega j in such a manner that zeta in both frequencies should be near to equal. Further, omega A and omega j should be chosen in such a manner reasonable values are represented in all modes. That is very, very important. You cannot simply pick up any arbitrary value of omega and I say you are distributing it for the entire structure. You must check whether other modes also have the relative zeta value or not. So, how to do that? Let us say for example, I have omega 1, omega 2 and omega 3 in my given problem. I pick up omega 1 and omega 2 for a specific zeta. Okay. So, when I pick up omega 1, omega 2 for a specific zeta, I fix omega I, omega j and zeta, I get A0 and A1, I get C. Okay. Then check back whether zeta 3 is also approximately equal to zeta 1 and zeta 2. That is, the zeta in the third mode is equal to 1 and 2 or not. We must check this. Okay, that is how we can satisfy. If it is not, change 1 and 2 to 1 and 3 and keep on iterating it and finding it out. Okay, it is very easy to look at the site here. We will take an example quickly. We will solve this in 10 minutes time. Let us say it is a long problem. I have got to find M, I have got to find K, I have got to derive the equation of motion, find omegas, find phi, find zeta and complete C and check at zeta 3 also. All has to be done in 15 minutes time for a 3D difference system model. Okay, we will pick up this problem. So, let us say I have an example. I call this as M1, M2 and M3, which are nothing but simply same mass. I call this as K1, K2 and K3, whereas K1 is K and K2 is 1.5 K and this is 2 K, where M is 3500 kg and K is 1500 kilonewton per meter. So, let us use Stored law to find out the fundamental frequency and mode shape first. So, you are an expert in Stored law method. So, give me the reply or answer for omega and phi 1 quick. So, M1 is M, M2 is M, M3 is also M, K1 is K, K2 is 1.5 K, K3 is 2 K, this description. So, I assume a deflection at the mass points. Then successively I get these values as omega square and omega square, then omega square, 2 omega square, of course M is common here, M is common here. Then I divided by the spring force, I get 1.5 M by K omega square, 1.33 omega square, cumulative deflection 1.5 omega square M by K common, (2.83), 3.83. So, I get a ratio of 1, 1.89, 2.55. So, that is the first band. These are the values. We started with 1, 1 and 1, we got some other value. So, they are not converging. So, iterate. Kindly do this and tell me what is the final convergence value, quick. We will give you 3 minutes time, otherwise write the answer here. So, by iteration, so I think we should say refer to lectures of module 1, okay. I have the converged values like this, M by K multiplier out. You please check whether I am right or wrong. 3.11 M square, sorry, 6.58, and 9.68. So, I have the multiplier as 1, 2.12 3.11. That is my final answer. These are converged values. At fourth iteration. So, let us quickly work out omega. I will do it here. So, 1 plus 2.12 plus 3.11 should be equal to m by k of omega square of 3.11 plus 6.58 plus 9.68. This gives me omega as 0.57 root k by m, and phi 1 becomes 1, 2.12 and 3.11. I will give you another 5 more minutes. You can try to work out omega 2, phi 2, omega 3, phi 3 using influence coefficient technique. That may take some time, you can verify it later. I will give you the answers now. Do we all agree with these answers at least? Is there anybody who has done these two answers or not? Yes or no? Yes or no? You try this. So, now I am writing omega 1 phi 1, omega 2 phi 2, omega 3 and phi 3. So, omega 1 was equal to 0.57 k by m, which will be equal to 0.57 of 1500 into 1000, that is Newton per meter, divided by 3500 kg. I get this as so many radians per second, which comes to 11.8. And phi 1 I am just slightly rewriting it in a different fashion, because I always wanted the top deflection should be unity with respect to which what will be the proportion of these, that is an order generally given, because I am always looking at the tip deflection in any system. Okay. So, but the phi what I had, the tip deflection was 3.1 whereas the bottom was 1, I am just reversing the proportion. So, it will become now 1. So, 2.12 by 3.11, which is coming to be 0.68, which is nothing but 2.12 by 3.11. Okay, I am just writing it here for our understanding, and of course 1 by 3.11 0.32. This is my phi 1 omega 1. Okay. Now, similarly for phi 2 and omega 2 and phi 3 and omega 3, I am writing the values here. .27 radians per second, and phi 2 was 1 minus 1 minus 1. There is only one 0 crossing here. Okay. From positive to negative, it remains negative later. So, there is only one 0 crossing. So, second mode. Phi 3 was omega 3 was 44.778 radians per second, and phi 3 was 1 minus 3.68 plus 4.68, 2 0 crossing, third mode. Now, the mass matrix, I will remove this. The mass matrix is a diagonal matrix, because my degrees of freedom are measured in the point where the mass is lumped, which is equal to m of I want to write the stiffness matrix. So, let us write the equations of motion and write the stiffness matrix for this. So, let us pick up the first mass m1 which is acting at x1, trying to pull it down, and this spring which was k1 will push it up, but of course with a relative displacement. So, I must say m1 x1 double dot is minus of k1 of x1 minus x2, which will give me m1 x1 double dot plus k1 x1 minus k1 x2 is 0. That is my, let us say, first equation of motion. Similarly, the second mass which is m2 is again equal to m moving downward by x2, whereas this spring is trying to push of x2 minus x3 as well as x2 minus x1. Okay. We already said you must use the first coefficient at the point where you are measuring and mark the arrow direction accordingly. Okay. So, the equation of motion in this case will be m2 x2 double dot will be minus of k2 of x2 minus x3 minus of k1 of x2 minus x1. Rearranging, I will remove this. Minus k1 of x1 plus k1 plus k2 of x2 minus k2 of x3 is 0. That is my second equation of motion. Similarly, third mass m3 which is also equal to m, I am pushing it down by x3, this spring which is k3 of x3 will push it up, whereas the second spring here which is k2 of x3 minus x2 will also push it up. So, m3 x3 double dot minus of k3 x3 minus of k2 of x3 minus x2, rearranging m3 x3 double dot minus k2 of x2 plus k2 plus k3 of x3 will be 0. That is the third equation of motion. So, pick up only the k terms, write the k matrix. I am doing it here. So, k times of, with x1 it is 1, with x2 it is minus 1, and of course x3 it is 0, is that right? Look at the second equation of motion which is here, with x1 it is minus 1, and already we know k2 is 1.5 times of k1. So, I should say plus 2.5, and this is minus 1.5, is that okay? Look at the third equation, with x1 there is nothing, with x2 it is minus k2, so I should say minus 1.5, with x3 it is k2 plus k3, 1.5 plus 2.5, so nothing but 1.5 and 2, so 3.5. This is my k matrix. Why I am interested in finding out m and k separately? Because to find C I must have a0m and a1k. So, I must have these two, otherwise I cannot find C. Okay. So, I have got m and k now, I have got governing equations for a0 and a1, I have got 3 omegas 1, 2 and 3. Pick up any two for a specific zeta of value assumed by us and check whether the zeta is conforming to the third frequency also or not. That is how we verify the Rayleigh damping, is it not? So let us do that quickly. We have only just about 3 minutes time, but still I want to complete this problem. I will complete this because any doubt here? Any doubt? So we have got equations for A0 and A1. We already know M is 3500 kg, we already know that, and K is 1500 kilonewton per meter, we know this, and A0 and A1, the equations were 2 omega I omega j by omega j plus omega I of zeta, whereas this is 2 zeta by omega I plus omega j. Is that okay? I am substituting it here, twice of omega 1 was 11.8, I am picking up 1 and 2, 29.27, I am working for 5% damping, 0.05, and of course divided by 11.8 plus 29.27. This will give me A0 as 0.841, you can check up that later. A1 will be twice of 0.05 by 11.8 plus 29.27, which will become 0.0024, very marginal contribution from stiffness, very major contribution from mass. So I have A0 and A1, I have M and K, I can find C. I want you to do that, but since we have no time, we take an advantage of that and give you the answer of C quickly. So C will be A0M plus A1K, A0 and A1 are known to me, I have M and K, I get C matrix as 6543.5 minus 3600 1194 point, sorry 943.5 11943.5 minus 5400 15543.5. This is my C matrix using Rayleigh damping. Now to check zeta 3, that is my whole argument here. I will rub this. We already know zeta n is given by this equation. So let us find zeta 3 for the known A0 value for omega 3, which will be 0.841 by 2 of 1 by 44.778 plus 0.0024 by 2 of 44.778, which gives me 6.3%, which is agreement with phi. So I can apply Rayleigh damping for this problem. Okay, that is how we will check whether we have taken the correct value. If it does not agree, keep on changing zeta, keep on picking different omegas and see, because idea is you must distribute the modal damping ratio for the entire structure. So hypothetically you pick up either large space frequencies or close space frequencies depending upon what zeta you want. Okay. So now this answers a major problem, that for a given structural system, for a known mass, for a known stiffness, I can assume zeta value, I can find omegas first, I can find C matrix, which is a combination of inertia damping and stiffness damping together. Okay. The next model what we discuss will also be applicable to FSI values, which is Cauchy model. Cauchy model is an improvement of Rayleigh damping. It says that let us add A0k, A1m plus something different. Why that is added, how it is added, how it is improved by Rayleigh, we will see in the next lecture.